So I thank RISC for giving me this platform to talk about some of my research. So this is about the use of GIS. You may have seen about the GISE lab. So this is some of the work which came out of that. So first of all, it is done by a lot of students and project staff. So Asim is a Bharat and I are faculty members. Asim is an undergrad student. There's a big team of undergrad students as well, and project engineers like Asim. So I'm going to talk about the problem. What is the basic problem and why we need an IT stack for it. And then I'm going to talk about a collaboration between us and Google Research, and how we collaborated on improving some basic segmentation algorithm, and then how we decide to use it for land records. Then the actual interaction with the Department of Land Records of Government of Maharashtra. What happened in that and where are we? And then finally we will end with sort of what is the message. So first of all, if you see the headlines, you'll see that Indian courts about 10% or depending on the statistics, about 10 to 30% of the court cases are about land, and they are about land records. And the main reason is that the record may say that this is land, but if you put it on the ground, then you see that there's a lot of mismatch between the actual record and where your piece of land is. So obviously, if there's a discrepancy between where you are farming and what the record says, if you want to build a house over in this corner, right, then you are going to be in a problem, right? So essentially, the mismatch between actual physical land and the records creates a lot of friction in the economy. If you want to change land use, if you want to grow some new crop, if you want to take a loan and so on. About 50% of Maharashtra's land have a discrepancy of about 20%. So it's a huge problem, right? So we really need to work on this problem. So the question of course is that how are these land records to be fixed? So first of all, we've seen, so what the proposal is to build an IT stack just for land records. So have we seen IT stacks before? Yes. The first IT stack is the transportation IT stack. We've seen Google has created, since 2000 we have this, Google Maps, and basically there is a transformation or there's a translation of reality into some data structure, right? So you have roads, you have places, you also have polygons and so on. And based on that, a lot of infrastructure is actually working on that. So for example, cabs, public transport, and in fact a lot of other things, finding routes and so on, is actually working on that infrastructure. So there is a layer, there's a ground, just as in computer systems, there is a base layer, then an intermediate layer, then an application layer, and all of these I have combined to give you actually useful services. So this is the one IT stack. Then there is also an agriculture IT stack, which of course what I'm going to do is part of that. And agriculture also needs a lot of inputs from various parts. The basic unit, the basic ground reality are farm plots, right? And on that there will be irrigation infrastructure, on that there will be energy infrastructure, then some commercial, where are the APMC markets, what are the roads, if I grow papayas, can my truck go into the farm and fetch the papayas and take it out of the farm and so on. So there are many questions which the agriculture sector also needs, and one of them is basic issue of land records. So the IT stack for any sector is actually built on the basic reality, then some application, then some intermediate layer, analysis layers, and then finally the application layer. So here is where we started. So we wanted AgriStack was an initiative started by Government of India, I think about 4 or 5 years ago, but we started work on this slightly earlier. So Anthrokrishi was a project, I think it has ended now. It has now been morphed or renamed as ALU, Agriculture Land Unit Project. So what it was is that, can we, given this image, which is of course several hundred megabytes, can we reduce can we cull out the important information so as to reduce the memory requirement, and also introduce a new conceptual layer, right? So can we introduce, I want to know whether this farm plot is accurate, what crop was grown, how much was the cropping intensity, does it need land, how much do you think was the yield, and so on. So we would like to build a conceptual layer above this, above the image layer, so that we can start working, so use it for operation. First thing is segmentation. If you look at this plot and somehow you sort of segment it, and this representation is a vector representation of the same image, right? And it's substantially about 100 times smaller in size, correct? So this segmentation, then once you do that, it allows you many other things, right? So for example, look at those segments and curl the, satellite image, right, and average out what is the green part, what is the average color of that particular plot. So here in this case, what I have done here is taken that plot and sort of smoothened out the image on that plot. So now I have an average, the average greenness of that plot, correct? And the next thing would be, how would you, if you have this average color, what would you do? Do some K clustering, correct? So if you do some K clustering, then you would get there are some 2 or 3 major clusters, and then by that you can actually say that, for example, that this was taken in December or November. So there are 2 crops. There is a kharif, which is soybean, and a long kharif, which is cotton or tur, correct? So by this, simply by segmentation, and knowing what the village and what are the major crops, you sort of have an understanding of what is the cropping pattern of that village. That so much of tur or soy cotton was there, and so much of soybean or moong or any other short kharif crop. So by the way, what is the kharif season? It is the monsoon season. What is the long kharif season? It extends, it extends beyond the monsoon. So it may typically be, harvested in December or beyond. So by this simple trick, we can sort of estimate what is the cropping intensity or how was kharif for that particular village. First question is how accurate our polygons. If you see here, so you'll see a lot of, there's a tree here, there's a well over here, and then there are, so there is the problem of segmentation, and different farms, different cropping seasons, then there may be orchards, right? There you can see here that these are, and different ways of furrowing. For example, haldi, the furrow size is much larger. If you have soybean, there is no furrowing, right? And there may be orchard like limbu, Mosambi or limbu, where there are actually individual trees which are planted in a lattice. So the image, just the recognition of the image and its classification over all seasons is a fairly hard AI/ML problem, and that was what Google research was doing. Our part was to give them the ideas or various metrics of how do you judge whether a plot is good or not. So there were many metrics for the plots, and one of them was variation metrics. So it is, given a plot, we sort of measure how much is the angle deviation, total angle deviation in the plot. So for example, if you look at this, the earlier picture, if you look at this plot, this is a much better plot than say this. So if you just count the total absolute value of the angles, right, and sum it all up, you will get one metric of how much is the variation in it. We had some other metrics of average geometric shape and so on. So based on these metrics, the plots were improved, right? And now I think, if you take these plots to the government, they're going to say this is not how my farms are. If there's a polygon, so it's basically how much steering are you doing? That's it. If you're driving a car along that boundary, how much is the angle steering that you need to do? Right? If it's a square, you just need to do 360. But if it's an L, then you need to do this, then you need to do, it'll be about, I think, 360 plus 180, 540. That metric tells you how much is the variation. So there are many other geometric metrics also which tell you what is the quality of the plot. But of course, it should match the reality, right? So there may be, so it depends on how many are actually L-shaped plots and how many are, normal rectangles. By then, what we did was to color these plots by their variation so that, bad could be quickly identified, and then it could be checked whether there's actually a recognition problem or the land actually is quite complicated. For example, a farmer may, divide his piece into 2 or 3 L-shaped regions, which are interleaving, so they do multi-cropping. So maybe it is that. So this sort of analysis helped the algorithms sort of focus and find, or fine-tune their recognition process so that it could improve. Other thing that has to be managed is temporality. Now, for example, Rabbi, you may, for Kharif, you may sow something. Rabbi, you may keep something fallow, right? Repartition your land. So next year, Haldi ka bhav was very good. So you devote a much bigger plot to Haldi, right? But it's the same piece of land, right? So you really need to, it's like having temporal snapshots and trying to interleave, trying to build sort of a tree. You are allowed to merge plots, subdivide it, but yet maintain the same geometric structure, right? So this is really important for the agri stack, where we need to track what is the farmer doing? What has he or she sown? How much sort of water did she need or energy she wanted?
Sorry, actually in the previous segment, so when you are doing clustering, so how do you determine this value of k, because this is correlated, right?
Correct. So actually they are we are providing the geometry. So they are using, various other, I just showed a simple K cluster.
Right.
They will, do a far more, I think there's some supervised learning, unsupervised various models and so on. So I don't get into it. But I just give the basic ideas that, given a plot, given an image and a plot, that plot has a certain internal correlations. Right. So we need to exploit them.
Right. Because I was just wondering that, like, determining that how many clusters is related to that what happens
exactly.
in the
that
next
needs
step.
Field experience. That's why we are here.
Yeah.
So for example, in a village, 2 or 3 are if there are 3 or 4 major crops, we should expect 3 or 4 major clusters. So here you will see that actually, how the temporality, for example, over here, this was one plot and it got bifurcated in the next season. So this also some examples and some bad, recropping and so on. And then we came up with a theory of something called super polygon. So it's like an equivalence relation on polygons, right, which we sort of use it to integrate. So it's in a way the coarsest possible division of the land and the finest possible division of the land, which will explain all the seasons, right? And that coarsest and the finest will tell us what is actually, land control. What land is owned by the farmer, right? So here, for example, if I see this, if I see this, then P1 and Q1 probably belongs to the same farmer, right? But if you see P2, Q2 and P3, this whole this whole blob actually quite likely belongs to a single farmer, right? Because you see that the decisions are actually overlapping, right? So this helps us, so these sort of equivalence relations and metrics help us understand how land use, how those land records are made. So let me tell you the history. So history, of course, the real serious land records started with Mughal era and they were called Zamabandi. So in a village, Zamabandi is the summation, total area, what is its crop and how much could be the taxation, right? So it was for taxation purpose where it was called Zamabandi. Then after that, the Britishers came and they brought Akarbandi. So what is the difference between Zama and Akar? Shape, obviously. So they started giving shape to those plots, right? So they started being drawing, but those were, so there was a village map and there were individual pieces of the jigsaw. Here's your land, here's that land, A's land, B's land, C's land. Did it piece together? Well, if it were made from a common map, perhaps, but that, the creation of individual plots and the village map, were actually parallel activities, right? And in olden days, this was this Moses Savangi, right? So this was a village map, and then what the government did was to scan this and produce something like this, right? So this is just a segmentation of that picture, right? It has no georeferencing, it has no latitude, longitude, no area, no scale, right? So the first job was to actually scale it, right? I know this is Savangi, so I have all those farm plots, so I put it over there and then I scale it, rotate it and so on and try and get it. So then once you sort of georeference that plot, then for example, even this plot was produced by our georeference, right? So we tried the best possible georeferencing and then superposition, and then we understand that this is the discrepancy, right? By the way, in their digitalization processes, they use scanners, and accidentally we discovered that the horizontal and the vertical amplifications are 3 or 4% off, right? That came, so we had to actually enlarge the, the family or the, group of transformations and allowed to do the georeferencing. We had to allow not only rotation translation, but also differential scaling, right? So that we could get the match. So if you look at this problem, right, there are these there is this land record and there is that image. So how does the Google ALU or the Procracy come? It provides us polygons for the piece of land, correct? So now we have one polygon and we have another polygon. So we can compare the two, right? And here is the comparison. See now that the segmentation and the land records together give us a very good picture about the mismatch. So this sort of, so if you look at this, this is a mismatch, right? So this should either, we need, so basically the two polygon matching becomes an optimization problem. From the image processing, which is really huge, which does not allow us to, formulate optimization problem, we have now come to an actual optimization problem. And what is that problem? So by the way, our actual land records are a complete mess. So if you look at this is I think this is Gadinglas, which is, South Maharashtra, so south of Kolhapur. So this is the mess that, this is the best possible fit. So you will see, for example, you say, why don't you shift this down? But if I shift this down, this also shifts down, correct? And if I shift this left, right, you get the problem. So it's a global, are the boundaries, are the plot boundaries, the land records.
The lines are the land records.
The lines are the land
colored
records,
part is
and and the smaller polygons are the farms.
So those orange polygons are
So
produced by
orange
the segmentation algorithm.
No, orange is produced by Google, to which we contributed. Now, if you see these farm plots are much better. Their Varp is smaller, the jiggy jaggy, daggers and stabs, all of them are gone. Okay, so it took us 1.5 years to get to this quality of farm plots. And then we sort of now started the matching. Okay, so the first thing when you have an optimization problem is to define the metric. What should be the metric? So we first said that the excess area should be the metric. So, if you have this, if this is your farm plot, this is your boundary, the black, and these are the farm plots, then what is the excess area? This part which is outside is excess, this part which is inside is excess. Now that I have an excess area, right, what do? I start with the cadastral or the survey record, and I start running something like a BFS. So I take a plot, I sort of shift it, match it, minimize the excess area, then take the next plot. So basically from a planar graph, which is the survey plot graph, I have an adjacency list and I start matching the cadastral and trying to fit it, right? So, but before we do that, after all, the survey plot is a area partition. You got the survey graph is a partition of the village area into, various plots. So they piece together as a jigsaw. But while our farm plots are not like that, right? So we need to, create a planar graph from the farm plot, and that is being done through this process of Voronoi diagram. So you use the Voronoi to create, from these plots, you create a planar graph. So now there are two planar graphs, right? And you are trying to impose one planar graph as a subgraph of the other, namely the, the survey graph, that's the official record graph, onto the actual farming graph, right? And using a geometric BFS to do it, right? So that was our strategy, right? So yeah.
So what is the metric for such Voronoi partition? This is not like, what is the norm?
No, actually there are many variations which we had to do.
Right.
You see, for example,
Because
the two farms may start diverging.
Right.
And there's a road which is cutting across one. So there are many, the actual problem is trickier. This is just the basic maths. Right. So now what do we have? One planar graph and we have the other planar graph. So this planar graph is coming from ground reality, the farms, and the other planar graph is coming from the survey record, correct? So one jigsaw and another jigsaw, and we are trying to match the two jigsaws, except that one is finer than the other, right? And now the records which are 100 years old, a new road may have been created, then the stream is actually changed by the farmer, because he or she wants the stream to behave and go, just by his boundary and so on. So there are many other issues. So anyway, this is what we call the jitter fit. So jitter fit basically is a BFS where you jitter, it tells you, basically the BFS allows you to schedule the next vertex or the next face to be matched, and then you sort of match it and then you move, right? So you jitter the next plot and the next plot and so on. So this is called the jitter fit algorithm. And then, so for example, here you see that so the red one was the initial one, and then the black is the jitter fit, okay? But of course there are some constraints. You cannot shift the plot, you cannot change the shape of the plot too much, right? You cannot make an L into an M, right? Otherwise the farmer says, it's not my plot, right? So anyway, there are some tricks. By the way, I will put up this presentation on my web page, so you can refer to it, whenever you want. So anyway, so we ran all of this, produced statistics and showed it to government of Maharashtra. Look, we can work on this problem. So they said, no, no, all this is fine, you are all researchers, but the real problems are quite different. So they say that in your case, when you are doing the jitter fit, the plot boundaries are matching farm boundaries, but there is a lot of encroachment. So actual farm boundaries need to move, right? And you have to respect the legal area. So for example, if there were two farmers, one was 200 meter long, one farm, another 200 by record, and this guy was staying in the district place. So this farm has grown from 200 to 210 meters, and the other guy has reduced to 190 meters, but the lengths, but the record says 200 200, right? So they said that farmers are very sensitive to change in formal records. So if it says 200, you have to give him 200 or her 200, right? So excess area minimizing and jitter fit has to be constrained further. You cannot really do as you want. Then also you need to identify areas where I need to do resurvey, right? So if you saw that Gardingler's map, there were zones of good, zones of bad. We need to do that, and then it does not merge with existing workflows. So anyway, they told us that there are 2 or 3 attributes which we must do. So you have just looked at possession, which is farmland boundary. There has to be legal validity, and there has to be operational feasibility. That after all, our workers have to go and stand there, between 2 warring groups of farmers. So you got to help us with that. So we understood their process, right? They have a long process. Then we identified where all IIT can work, so actual working with an agency, understanding their SOPs, their legal frameworks and so on. And then we came to, the new design. So there were 2 new inputs. One was the legal land record, right? So there was a polygon, there was a shape of the polygon and some legal, how big is that land, right? And that also they needed to excavate various dusty files in various offices, take them down and then prepare it. So they did that, right? And the second thing is GCPs, ground control points. So maybe in a village, there may be about 8 or 10, pillars, right, of which the lat longs are already known. But what they didn't know was that, for example, this pillar is in the boundary of plot number 34, 35 and 36, tri-junction pillars. What I would like is, in my BFS, so if I've done plot number 34, 35 and 36, that there is this particular pillar, which is a tri-junction of these 3 plots, and its lat long is known, so I need to, pitch it there. That is what I would have liked to do. But they didn't have that. They have the lat long of that pillar, but not the, the plot numbers. That is plot number 34, 35, 36. So the geometric and the combinatorial linkages were missing. So that now they are trying to do, right? So this is going to be a long process. Anyway, the other thing they said is that, these are the new metrics. So the new metrics is the GIS area and the Akarband area should match. Number 2, the shape should not change, right? And number 3, there is the distance to bund. So instead of excess area, they said, you should give me an indication that the farmer needs to move his bunds by 5 meters, right? So that the area between the legal area and the farm area matches. So the distance to bund was the new metric which they suggested. So just to show you an example, so here you see the distance to bund is 4.54. This is the distance to bund, this, right? And in the new fit, the distance to bund is 1.48, correct? So it was not, the objective was not to minimize the excess area, right? The objective was to keep within 3% of the legal area and minimize distance to bund. Is that clear? Right? So they said ki, this 1.48, the farmer now has to fight with the neighboring farmer and resolve. We are not going to do it. But if it's like more than 3, like 8 or 10, then we will step in and resurvey. Okay, so the work was sort of partitioned between the farmers and their neighbors and disagreement and agreement, right? And so the metric was really how much, because that is what the farmer, you have to move your bund by 2 meters. Okay, I will do it. Right? You move your bund by 10 meters and there's a well, then he or she is not going to do it, right? It needs a resurvey. So these are the change in metrics, right? So they have a survey map. They wanted how good is my survey plot, right? So in terms of, so this is the actual area, the legal area, right? How much have we allotted it in our new map, and how much was the legal area, and then the farm rating, distance to bund. So this was the basic structure, and we did this, and I will not go into the details, but there's a pipeline which is now running, and MOU, and we have given them that pipeline, and they are working. But they are, of course, they are not IT engineers, so they are revenue masters. They are basically, so they are not used to this way of working. Setting up the cloud, then setting up some SOPs of how to do it. Even the data that we have to provide them with data analyzers. So if they upload the data of a village, then we say, oh, this is not textual, but this is actually numeric. This is numeric. Starting from everything, you have to help them get the thing right. So we've of course told them that you should hire an IT major, and we should be the technical partners, but they should actually take you through. But that's going to take take maybe I don't know how much time it will take. But anyway, so what we did was, overview of the problem statement, and then a huge pipeline. So I think algorithms were changed, and so a new concept which they introduced was that there are some plots whose ownership has not changed that much, right? And those plots, they are the most accurate, right, in that village. So there may be about 7 or 10 plots. Can you identify those and try to build your map around them? So what we do is we actually they are called anchor plots. So once we identify the anchor plot, the other village map is like a rubber band, piece of rubber which is sort of stretched and fit into the area. So anyway, so validation was done, and then basic. I think I've explained all the metrics. Some are really bad villages. I mean, look at this, right? Look at this. So I mean, there's no way. So they also understood that the problems are big, and that it actually needs a new act, a new act of the government to actually resolve these problems. So this is how how the heat maps actually change over time, or in our algorithm. So what we get and what we output, correct? So this is, and these are the, so anyway, so MOU 1, so MOU 1 for finished last October. It was, I think, about MOU 2 has started. In the MOU 1, we did a pilot of about 150 maps, right? Then MOU 2 is about 6 talukas, and that's about 700. There's also the road network. Then they want to see how is the quality of GCPs and so on. And I think a new company was formed, an undergrad student, right? So that's Aryan. A lot of the work was done by students in my data structures course, CS213 and CS213M, right? So a lot of the students are from the minor version of the data structures course. CS students, I think we will do financial, quant or whatever. So, but the CS213M, the minor students contributed a lot to it. But this guy was a major student. Okay, he was a CS student, and they have now formed this company, and it's also doing a lot of other things. So it's called TerraStack. So you can look up TerraStack, and it has now come up with a Jalgaon district, everything, right? So you can look at what all data it has to offer. So anyway, Bharat is there, Asim, Ilisan. We also presented this work at the American, I think, Geographical Union conference, and it was invited to make a presentation, not just a poster. So here's a peek into our team, right? So there's a lot of good food also, right? So a lot of fun, and looking at land records. I mean, for example, Himachal. So I'm doing another project in Himachal. The land records are called Latha, and they are on big canvas cloths. It's about like 10, 3 meters by. So it's held like this by 4 or 5 people, and then the plot is identified. Okay, so very interesting. Listening to IS officers give fun days, right? Then fighting with ourselves about data structures, what it means, and so on. So what's the message? Really, something as simple as a map is actually quite a interesting object. So by the way, I mean, I really like maps, fine. So one other project which we are doing is for Lanja Taluka, which is a tehsil. We made, we've surveyed all the roads from Wadi to school, from school to bus stop, and so on. So these are students who are surveying, right, doing field work. and producing these maps, correct? And then the whole village taluka map. How good are our roads? What is the investment which is happening? Correct? And put them up in the school. So here is a video. Can you play the video? So there are students watching their village. Oh, this is my wadi, this is my house, here is how I walk, and so on. So this is our worker who explains the map to the school students. And the girls and boys, everyone's really curious. They've seen their own village map for the first time. They've seen India map, district map, and so on. But they've never seen a map of their own village. Okay, so let me stop here. Any questions?
Suppose land parcel contains a hill or a depression and the boundary runs through it.
Yeah. So in fact, the non-ag land, in a village, is a good indicator of how complex the land is going to be. So that is a separate, that has to be handled. So in fact, the farm boundary and so this is part of the river, road, non-agriculture land. Basically, we had to understand land use as well. So the actual now algorithm uses land use.
How about the tea bagans of like Assam and all? Because you said first you basically divided it into the crops. So there is only tea.
No, not crops, polygons. Whether it's cropping land or not cropping. Recognition of the crop is a new product. So this is ALU, just land parcels.
Okay, so basically recognizing what crop is happening is not a part of it.
No, so this is in the new year.
Okay. Thank you.
But you see, identifying the boundary, you see, given a image, recognizing crop for that image. But if you have a piece of land which we know is the same crop on that piece of land, the recognition problem becomes significantly easier. You have this particular piece which we know there is an additional information that in this part of land, the 2 points, 2 pixels are indeed, should give you the same, whichever K mean or whatever you have.
Crop is same in like a very large area and farmers will have smaller plots
so that
allotted to them.
The subplots are being identified.
Plots are identified from the government records
No,
Google
from
Maps.
the image.
Okay.
Right, from the image, if the farmer has, so, individual farm plot parcels are identified. So essentially the ALU algorithm has that, that the similarity between 2 pixels is coded into the, so it is not based on segmentation actually. Okay. So that's the thing, that it is on a, it's like an ant which is walking across. So it has some history. So ant which is walking across the land and which is recording some attributes of that property of that which have to remain the same. So it's a, it's a more dynamic algorithm. So it's not really based on segmentation.
DTB matrix.
Distance to bund.
Okay.
So distance to bund is excess area divided by active perimeter. Right. So what is the excess area? But you sort of average it out over the active perimeter. So that gives you that roughly 2 meters you have to move.
Yeah. So what is the end goal of this? So at some point, are you going to tell all farmers at one point ki,
I am not going to tell.
I mean, the government is it going to kind of
land records needs to get its act together.
I mean, so at some point are the boundaries going to be moved for everyone?
So we would like to. So what, I mean, I've also talked to government of India. What they're saying, okay, these maps are good. Publish these maps for 6 villages and prepare for revolt.
Exactly. That's what I was wondering. Because if you change boundaries for everyone.
Basically, they want to understand what, so we have regions of poor records, poor surveys. So those, once you say ki now publish these maps for 6 villages in 6 divisions, then the problems will come up and then the new act will be framed. Essentially what is happening is if it's instead of 200, it becomes 180, 220, then both plots are bad. But if taken together, they are good. Is that clear? So it is really that if those 2 plots are joined, then it's a very good plot. The DTB is good. So it means that there's an internal redivision which has to be done. So then they can say, oh, you 2 guys just sit down and now get your act together. So there are new features which we need to add.
Sir, given the unpredictability of the monsoon patterns in India,
Yeah.
can geospatial technology or the work you are doing, can it be implemented to mitigate the impact of the climate change on crop production?
So I think you should look for POCRA, P-O-C-R-A. So we've been working with Government of Maharashtra last 5-6 years and last 2 years with Government of Himachal Pradesh, essentially to build village level water budgets, right? And help farmer, for example, if there's a soybean crop and there's a 3-week deficit, there's a 3-week break in the monsoon, what would be, how many irrigations and how is the village capable of supplying those protected. So look at on my webpage, POCRA, P-O-C-R-A, Project on Climate Resilient Agriculture. Okay, so that's a World Bank funded Government of Maharashtra project and a World Bank funded Government of Himachal project. And it's basically running, biophysical models, because we have the remote sensing data and we have the administrative data. So we know in this village there's a percolation tank and its capacity is so much. And in this village soybean is being grown and there's a 3-week, break in the monsoon. So many cubic meters are required and so many cubic meters are there.
Let's thank Professor
Thank
Milind for the talk. Thank you so much. We'd like Professor Varsha to just felicitate.
I just wanted to add to what he said. I don't think his bio was told properly. So he's BTech Computer Science, 1987, 86, and then Masters from Chicago, University of Illinois, and then he came back here and completed his PhD here in IIT Bombay, and then has been with us. And yes, it's quite a journey from the Milind Sohoni geometric complexity theory, something I only know the buzzwords. From there to a lot of problem solving in water, in land, climate. He's also, what is nice, the phrase public intellectual. He's a public intellectual in the sense that he writes very frequently in very major newspapers like Indian Express. I would encourage you to follow. Just Google Milind Sohoni. There's a continuous list of all his articles that you will get. Very thought-provoking ideas about all the sorts of things. What should computer scientists and engineers in this nation do? He has a lot of ideas about that. So there is a lot more to Professor Sohoni than we saw just in the 30-40 minutes today. So thank you, Milind. Really, really great talk. Yeah, thank you.
What we hope from RISC is, I hope that what we hope from RISC is actually achieved, and a lot more clever students start working on these really hard, intellectually hard and stimulating and still scientific problems. Thanks.
Okay.